Swayam Prabha. Digital India. Educated India.
Okay, we'll go on with the discussion on Langevin equation and Brownian motion. So, the last time I was telling you that whatever you derive from these two, they should turn out to be the same. We went ahead and derived the expression for the mean square displacement and then the RMS, right, and we said that the RMS is the one we should really care about, because we saw that the average of x was essentially 0, right, because it was an odd function. So, this is what we derived. So, this is the probability distribution for a random walk, right, where you are moving a distance x, does not matter in which direction. You are given n steps, where n is the number of total number of steps you are taking. So, this number 18 is typically a Gaussian distribution. So, if anyone has to talk about trying to model a random walk, then the thing you would start with is a Gaussian distribution, because that is what best describes someone actually executing a random walk, right. And then we went ahead and said, or we derived actually, that the average of x square is equal to n, and hence the RMS is root over n, and this is where the random walk stands out, and this is what the last few lines say. So, this, which is equation number 20, this means equation number 20. So, this means equation number 20 is a characteristic feature of random walks, and the RMS displacement from the origin scales not linearly as a number of steps, but actually as a square root, right. Again, this is a characteristic of someone exhibiting random walk. Now, let us consider this. How do you do, or can you have a relationship between fixed law and random walk, in the sense that, see, what we have said is average of x square is equal to n, right. Now, when we consider fixed law, what did we say in fixed law? We did not talk about the number of steps, but what we talked about was your concentration profile in terms of a diffusion coefficient d. Is there a relation between n, which is the total number of steps, and d in terms of something? Now, if you think about it, there should be a relation. Why? Because you take a certain number of steps, or a molecule takes a number of steps in solution, and that the number of steps it takes would also be in some way related to the diffusion, because the molecule has to diffuse to take the number of steps, right. So, then there has to be an underlying relation, or something which is going to connect both of these, right. So, if we try to look at that, what we consider is, you take a drop of dye in water, right, and then you observe its spreading. So, spreading essentially is by diffusion, right. Then what we would need to solve is, we would need to solve fixed law of diffusion, okay, and this we know. And what we take here is the second law, which connects the time dependence of your concentration change with the rate of change of the concentration gradient, which is del 2c over del x squared by the diffusion coefficient. Now, if you solve it, taking certain assumptions, about the initial conditions, what you get is the c as a function of x and t varies as this. The constant is c0, c0 or c0 is essentially the time, initial time, say at t is equal to 0, right, when x is equal to 0. Then in the denominator you have square root under square root 4 pi d times t. Now, look at the next function. The next function is e to the minus x square by 4 dt. Now, is not this also Gaussian function? See, this is also Gaussian function, right. When we derived the random walk from actually looking at a random walk problem, right, taking n number of steps, or n1 number of positive steps, n2 number of negative steps in the negative direction, you also ended up with the Gaussian distribution. Here also you are ending up with the Gaussian distribution. Now, to try to bring about a parallelism in these two, what we do is we say, suppose the dye molecule starts at x is equal to 0 when t is equal to 0 and now takes n random steps. So, now think about it like this, the dye is diffusing definitely, but forget about the diffusion for the time being. What you are saying is that the dye started at time 0 at a certain point where x is equal to 0, arbitrary, does not matter, you have shifted the origin and said that x is equal to 0. Now, the dye diffuses means it starts taking a certain number of steps in a random direction, because there is no bias. Okay. Then obviously, the concentration of the dye can also be expressed as a random walk model, right, and if I do that, so this is what you get. So, then see x as a function of x, then the total number of steps n is given by this probability distribution. Now, this you know from before, this you do not have to derive again, okay, this you know from before. So, then you have two relations, one is c as a function of x and t, and the other one is a random walk problem c as a function of x and n. Okay. Now, both of these are equivalent, see both of these are Gaussian functions and both of these end up describing the same situation, telling you the same picture, only in one case you have a time dependence and the other case you have a step dependence, right, x being the same, that is the distance being the same, x. So, then what does it mean? What it means is then there has to be a relation between the number of steps you take and the time, obviously, because taking a certain number of steps you would be needing some time to do, and what should it be related by? It should be related by the diffusion coefficient d, by some relation or the other. So, now if you would compare these two, just compare 22 and 21, what you see is everything else is the same, right. Then you can compare this c, 2 n is equal to 4 dt, right, or root over 2 pi n is equal to root over 4 pi dt, these should be equal. When you do that, this is what you should be getting. Comparing equations 21 and 22, right, then n is equal to 2 dt, right, n is equal to 2 times d times t. Okay. Now, this is important. Here what you have said is the total number of steps that I take or anyone can take is equal to a certain constant times the diffusion coefficient times the time that is evolved since you started walking, since you started making a first step. Okay. So, then what I can say is, from before we saw n is equal to average of x squared, right, and hence now it is easy, x square is equal to, or average of x square is equal to 2 dt, right. Now, did we derive this before by some way or the other? We derived it using what? We derived it using the Langevin equation, is not it? We derived this using Langevin equation and this is what we got. When did we get this? We got this when t is equal to what? Long or short? When t was long, really long, right. Then you had sufficient number of Brownian collisions, that means sufficient number of collisions, and hence it was totally uncorrelated, and that is what it was defined by. So, that means using this random walk problem too, you reached the same conclusion as you got from the Langevin equation, where average of x square is equal to 2 dt. Okay. So, for 3D what will happen? So, for 3D what will happen is, see it is average of x squared. If you take 3D coordinates, what will happen is, instead of x you represent it by r. Okay. Now, instead of x if you represent it by r, then average of r square is equal to what, or r square is equal to what, you tell me. For 3D, r square is equal to x square plus y square plus z squared, right, and x, y and z are independent of each other. Now, if we have this, that means we know that average of x square is equal to what, 2 dt, average of y square would be what, 2 dt, average of z square will also be 2 dt, right. So, then what will the average of r square, this is essentially 3D you are talking about, would be 6 dt, right. So, this is what you have here, an average of r square is equal to 6 dt, okay, plain and simple, because these are not correlated, independent of each other absolutely, and hence we can always make this. So, here I can write this average of r square is equal to average of x square, y squared, z squared. Now, you can realize this, that a very general expression a very general expression from here would be, if I write r square is equal to 2 times d of t, where d is what? Where d is what? Where that small d is referred to as the dimensionality of your problem. The small d is referred to as the dimensionality of your problem, right. So, this d is referred to as your dimension or dimensionality. That means, if it is one dimension, then d is equal to 1, you get 2 dt. If it is 3 dimensions, then what is going to happen? D is equal to 3, you get 6 dt, and so on. So, it is generalized to any dimensions you want to look at, only keeping this in mind, that all these motions are independent of each other, they are not correlated with each other. Okay? That is how you can separate these out, they cannot be coupled. So, that is about random walk, its relation to Langevin equation. So, you can see that both Langevin equation and random walk are interchangeable, that means they talk about the same type of motion, which is the Brownian motion. In random walk, we started with the Brownian motion, you started with the n number of steps, right. You took this binomial distribution, you went ahead and solved it. How did you bring about the randomness in a Langevin equation? What did you do? You did something. You introduced something known as a random force f of t. That was the randomness in the Langevin equation, and in the random walk you actually had that binomial distribution. You started with these assumptions, and because it is a random walk, or because it is a random fluctuating force or random force, hence both of these should end up giving you the same thing, and that is what you just saw. Okay? So, it does not matter what you start from, it does not matter what you start from. One, you start from the Langevin equation, you knowing what Langevin equation is, and the other one you actually start from what a random walk is, or how you can actually describe a Brownian motion from very first principles based on a probability distribution. Does not matter what you do, you end up getting the same thing. Okay? So, this is mostly about diffusion, and please at least try to remember these things, because no matter what you do, you will always face these problems, because diffusion is so inherent, so fundamental to any process, be it a chemical reaction and be it any other reaction which happens in our body. Now, physiologically, that is why random walk is such an important phenomenon, it is really important. Okay. Now, this problem I want you to do by yourself. What will happen if you know that you have diffusion, and during the diffusion that process is also coupled to a chemical reaction. So, what I mean by that is, suppose you have a tablet, right, you take a drug tablet like a medicine, and there is a drug in it, and you know that the medicine is going to go somewhere, it is going to release the drug, and the drug is going to react and then have its effect. So, you have two things. What do you have? One is the reaction, definitely after the drug is released, but before it is released, then the drug has to diffuse, right. So, then you have the diffusion. So, then your total reaction, your total flux would be composed of two terms. What are the two terms? One is coming from diffusion, essentially the Fick's law, and the other one would be coming from the chemical reaction. Okay. So, here as I said, you consider drug molecules diffusing out of a tablet, you model it as a planar wall into a solution, and it is given that the drug molecule does undergo a chemical reaction according to this process. The dC by dt is equal to minus k reaction times C. Now, this is given to you. Okay. Now, what you also know is that now your change of concentration with time is not only your chemical reaction, which you do in terms of kinetics, right. In kinetics, that is what you do, right. You relate your change of rate constant and whatever to your time dependence of the change of concentration, but here you have a second term which is the diffusion, right, it is coming in. So, this is what you need to solve, okay, solve by yourself and see what solution you get, right. You can take any assumptions you want. By this by this time you must be knowing how to solve differential equations and what initial conditions you might want to start with. Okay, it is not an issue. So, try this out please and let me know. So, this is a homework problem. Okay, and write okay. Now, the last bit in this diffusion is somewhere which is also of very fundamental nature to us in biology. You look at this. When matters diffuse, right, that means you just have concentration gradients, your diffusion is occurring. But remember, your matter can be composed of two types of particles. One is particles which are not charged, right, neutral, and there can be particles which are charged. Now, for charged particles, along with concentration, what else do you have? What would charge give rise to? A certain potential. That means, for a charged particles, you would be having something known as a potential gradient. Now, I do not know whether you actually derived Nernst equation before, but Nernst equation starts from that. That is what Nernst equation relates you to. It relates what? It relates the change in potential to the difference in concentration you have. That is what Nernst equation does for you. So, you can see the last bit of this puzzle is ion flow or ion transport in our body, and specifically where is it important? You think about this. Our cells are lined by plasma membranes, right, biological membranes. Now, these are typically what? Hydrophobic. So, they are impermeable to what? Charges, that means ions, and we know we have different flows of ion, flows of different ions, right, potassium, sodium, calcium, chloride. How do you think these traverse the membranes if they are impermeable? How do they do that? Potassium? No, but potential would be there, but if the membrane is not allowing you to penetrate through, it does not matter whether you have the potential gradient or not, right. You have to be able to diffuse through that. What helps you in that? No, well, signal is there, the potential gradient is a signal. Ion channels. See, in your membranes what you have is you have different ion channels, potassium ion channel, sodium ion channel. Now, these are the ion channels which open from time to time depending upon your need, depending upon your signal. That is essentially what happens in neurons, and that is how these impulses take place, right. So, these ion channels open up and then allow your ions to pass through, otherwise ions are actually impermeable, they would not be passing through. Okay. So, that is what we would look at. So, this is what our next topic is. It is electrochemical potential and ion transport, and I will go through the initial phase a little bit fast, because these things I think you know. We start from general thermodynamics, and from thermodynamics you know, if you have an open system, where even matter is exchanged, that means matter transfer is going to take place, then the differential of G is essentially a function of what? G is a function of P, T and N, when N is the number of molecules, number of moles which can be transferred, okay, across whatever you are looking at. So, then dG as a differential would look like this, right. The first one is del G over del T at constant P and N, Ni times dt and so on. Now, this is where you consider only the molecules moving out, does not matter what these molecules are, they can be charged, they can be non-charged, right, any type of molecule. But remember, we have to bring in this electrochemical potential. So, this can be further written as dG is equal to minus S dt plus V dp sigma I mu I dni. Now, this you all know, right. Now, what you do is, as I said, along with matter transport in biological system, we also have charge transport, and if you have charge transport, then your potential is not only P, T and N, it will also depend upon Q, right. So, that also has to be brought in. Okay. So, if I try to bring that in, this is how I do it. I have to introduce electrostatic potential in my free energy problem, and the way I do it is, I consider a charge Q, any charge, does not matter what it is, and then I say that the electrostatic energy on this charge is given by Q times psi, where psi is the electrostatic potential, right, and this potential it can experience whether by a single ion being close to it or by a cluster of ions, does not matter, it is the net electrostatic potential it faces, right, being very general. Now, if that is so, now what I can do is, I can take that invoke it in this the free energy equation. So, up till this you knew from before, now I have this extra term coming in, psi dqi. Now, please note this difference. So, this, see, this variable is j and this variable is I. Tell me what does this difference signify to you? You know, what is the importance of this difference I and j? Okay, j might refer to any species, right? Then what about I? I will only refer to charged species, right? Because remember, you have dqi. If it is not charged, then dqi essentially is 0 for that. There is no charge difference anyway. It's a neutral molecule. It's a polar. It's not a. It's a neutral molecule. It's not a charged molecule. So that means the j and I differentiate you from what? From the charged type, from the essentially the non-charged type. But this d and I or the d and j includes anything and everything. And the last one includes only those ones which are responsive to a potential gradient because they have charges. Because your neutral molecules would not be responsive to potential gradient. They just don't care. Okay. Right. So, going ahead with this, let us consider that the total charge, say on species I, is given by qi is equal to zi times ei times ni. Now, this you know, it is not a big deal. So, what z is essentially the valency or the charge per ion, e is the unit of charge, we know this. Now, what about n? N is, say suppose I have a specific ion of type I, there are n number of those ions. Okay. So, then the total charge is this, it is not for one, but n number of ions. Now, if that is the case, what I do is I take this assumption. What I assume is in that dg, in that equation or differential equation for Gibbs free energy, I say that only those particles are moving across or are diffusing which are actually charged, right. So, now remember, how did we differentiate I and j? We differentiated I and j saying that I was essentially only the charged particles and j was the whole thing, because j does not care, it is just a matter of transport. The moment I say that only the charged particles are going to get transferred, then what do I say? What I say is that I is essentially equal to j, right, because now I can remove the label, I can remove that index, that labeling index, I can easily remove it. So, then the free energy becomes minus s dt plus v dp. Now, I am combining the two terms. Okay, one is mu y dni and the other one is z I e psi dni. And why I say z I e psi? Because of using this, where we have used dqi is equal to z I times e I times dni, where the difference or the differential of charge is essentially because of the difference in the number of particles or the number of that species I. Okay. This I take and put in equation 3, and this is what I end up with, which is equation 4. Simple, right? I just added these up, and in doing so what I did was I said I was equal to j, because those are the only species, the charged species are the only species which are getting transferred, right. Now, tell me this mu y, if I cover this, then mu I is your chemical potential, right. So, what does chemical potential tell you? The chemical potential tells you the potential of something to happen chemically, right. Now, if I take mu I plus z times e times psi, what can I label it as now? Remember, along with the chemical potential, I am putting in something else, which is right, which is electric potential. So, then in combination, what can I call this? That means I can take this and combine this with this, and what can I call this together? We can call this the electrochemical potential, right. And having used that, having said that, so this is how I say, you define mu I, this actually is not a comma, this is a dash thing, it is mu I prime as the electrochemical potential, then this can be written as mu I prime is equal to mu I plus z I e times psi. Okay. And what is the essence of this equation? At constant T and P, for uncharged species, equilibrium is only maintained when you have constants in chemical potential. Now, remember, this is for uncharged species, but the moment you have a charged species in, you cannot only talk about a chemical potential, you have to talk about a chemical of an electrochemical potential, right, and then your definition of equilibrium changes. Then for charged species at constant P, so this I would get rid of, for charged species at constant T and P, then equilibrium is attained when electrochemical potentials are equal. Now, this is extremely important. Why is it important? One, obviously you have to have equal electrochemical potential, but remember, whenever you are talking about a charge, whenever you are talking about charge transport, finally what do you have to have? Remember, there is a very stringent condition. The condition is, no matter what you do, you have to have charge neutrality. That means you cannot just rampantly take positive charges out without replenishing it with something else. Okay? That means you have to have a total of, the charge neutrality should always be maintained no matter what you do. Okay? Now, that is a very stringent criterion on electrochemical potential. So, having said this, having tried to develop this, introducing the electrochemical potential in Gibbs free energy, how can we get to Nernst equation? I am sure you have done this, but I will just breeze through it. You take two positions like this, okay? Say one is x1, the other one is x2, and you are saying that there is a potential gradient across this, and you need this potential gradient for a charged species to go across. Okay? And you say that the electrochemical potentials at these two places are psi x1 and psi x2. No problem. So, assume that only one type of species is moving, that means there is nothing else, only one type of species is moving, and hence what I can do is I can get rid of I, because there is only one species for me. I do not need to label it by I. Then at electrochemical equilibrium, what I should be having is what? At electrochemical equilibrium, I should be having equality of electrochemical potential, isn't it? If I have that, now this is what I have. That means at electrochemical equilibrium, my electrochemical potential at x1 should be equal to my electrochemical potential at x2, provided I am talking about the same species and they are in the same phase, right. That is how you define your chemical potential too, when you are talking about phase diagrams and all these things, right. Okay. Now, let us go ahead with this. Mu, the electrochemical potential, can be expanded like this. So, this was your initial mu I, which is the chemical potential, because that only depended upon the concentration gradient, right. The next one is a charge gradient, right. So, that is why what you have done is you have expanded mu I in terms of the mu I naught or the mu naught and the kT times ln C, that is how it is defined, the chemical potential. And if that is what you do, then what you do now is you consider mu naught to be independent of x. It is a constant, it does not depend upon x, no matter where you go, it is always constant. X1 and x2 are in the same phase of matter. You use this equation in equation 6, that means you use equation 7 and equation 6. Equation 6 was where you had said that the electrochemical potentials were equal, that was the previous equation, that was mu prime at x1 was equal to mu prime at x2. Then what will happen? Simply what will happen is, here you can write mu prime x1, right. So, here you can write mu prime x1, you can also write mu prime x2. If it is mu prime x1, then this would be ln C x1 and it would be psi x1, same for x2. So, let me go ahead and see, you will be having this equality, where you are saying because the electrochemical potentials are equal, these have to be equal to, right. Now, it simplifies how, because mu naught had no dependence on x, it is a constant, it cancels out from both sides. So, you are left with, you can see what you are left with, you are left with a concentration gradient, or you are left with two concentrations C1 C2 or Cx1 Cx2, and you are left with what? The electrochemical potential psi at x1 and psi at x2. So, if you combine these two, what you are going to get is a relation between your potential gradient and your concentration, right. So, that is what your Nernst equation is, isn't it? So, that means if you go ahead, this is how you can simplify it further, okay. This is how you can simplify it further, and having simplified it, what you write is the concentration at x2 is given by the concentration x1 times e to the power minus z times E del psi over kT. where del psi is essentially what? Your potential difference or your potential gradient. Okay. And C x 1 and C x 2 are the concentrations at the two borders. So, where we have used, so here we have used del psi is equal to psi x 2 minus psi x 1, that is we have done, and what we can say is equation 9 is a Nernst equation. Okay. This is what you know in terms of being a Nernst equation. That is how Nernst equation is derived. I am not sure whether you did this in your class in thermodynamics when you did it before, right, in the first year, but this is one of the most direct ways of deriving Nernst equation. Now, what I will show you later is I had to do this because to be able to connect it to something we are going to do later in class. You can also derive the same thing if you start from flux, because diffusion is all about flux, and if you are talking about flux, then again this flux would be having two components. One is because of your concentration, the other one is because of your potential gradient. So, hence if you are going to get Nernst equation like this, you should also be getting the same thing from there, maintaining equilibrium conditions. Okay. So, this can be further simplified as, I will just go ahead with this, where delta psi can be written as this minus k T over Z e ln C x 2 over C x 1. Now, moving it to a more familiar form, which you know that R is equal to n times k, the Faraday F is equal to n times E, right, it is 1 mole of charge, that is why it is coulomb per mole, and if you invoke this, if you use this in this equation number 10, and this is what you end up with, delta psi is equal to minus R T by Z f ln C 2 by C 1. Okay. So, again Nernst equation, that is why it is so fundamental. It not only tells you something on the electrochemical potential, but what it does is it relates the concentration, or rather the electrochemical potential gradient to your changes in concentration. Now, why it is important? Have you heard of the term resting potential in biology? A resting potential. A resting potential means if you would put in electrodes, say across any particular cell, say neuron cell or any cell, you would see that you have a certain potential which you will measure, say minus 70 millivolts or whatever. Why do you think this resting potential comes out? Based on this, why do you think this resting potential comes out? Here we are talking about only one species of ions, right? Say only your potassium channel is opening and only potassium ion is moving in or out. Okay? Only one species is moving in or out. Okay? No other channel is open. What it means is, then if you have a resting potential of a certain whatever value it is, that means you have a delta psi, right, which is a potential gradient. So, then what does this potential gradient tell you immediately based on this equation? What I am talking about is, I am talking about a potential gradient between the interior of your cell and the exterior of your cell. Okay? So, that means in between what you have is you have the plasma membrane, which is a lipid bilayer, then this is the interior and this is the exterior. Okay? And if you are putting into say electrodes, then you are going to register a potential, that means there is a flow. Why does this happen? Now, based on Nernst equation, tell me, why would it happen? Why would you get a potential difference? Because of concentration difference, which immediately tells you that the concentration of that species in the exterior of the cell is different from that in the interior, right? See, and that is what signaling is all about, right? That is what signaling is all about. You have a concentration gradient and immediately you get a potential gradient, and that is what your resting potential is. Now, there are different ways of measuring resting potentials, but that is a different issue. So, then this was something we always have to keep in mind. In a process involving electrochemical potential, electroneutrality always has to be maintained or always has to be preserved. You have no other way of going around it. Okay. So, this is what I was talking about. If you take selective ion flow, if you are talking about selective ion flow, now these are some examples I took, and this is what we were just discussing. You look at the ions. So, the leftmost column is your ions, potassium, sodium, chloride. The middle column, which is the second one, is the intracellular and the other one is extracellular. So, you can immediately see what happens, what is happening. Potassium ion is very high in intracellular, very low in extracellular, right. Sodium is just the reverse. Now, this you would expect why, based on some sort of neutrality, right, because you have so much of high positive out there and so much of low positive because of potassium. Then for sodium it would be the other way around, and then you have chloride, okay, which maintains the total neutrality. Now, considering what we were discussing just now, suppose only potassium was being transported across your lipid bilayer, because right now you know there is a concentration gradient, there has to be. Okay. So, then going ahead, what we say is that biological membranes separate components having very different ion compositions, and that is why your resting potentials come around, because you have differences in ion concentrations, right. So, see, very simple, it is based on Nernst equation. That is why Nernst equation is so important to biology. Rather, to be more specific, is so important in physiology. Okay. So, just a little bit of membrane potentials. Biological membranes have unique protein pores called ion channels, say potassium ion channel, sodium ion channels, that facilitate the movement of ions into and out of the cellular interior, because your plasma membrane is essentially impermeable to your charged species. So, they have to be able to open up, which is the potassium channel has to open up to allow potassium ions to pass through, otherwise they will not be able to do it. Okay, so, consider the case where the membrane is only permeable to potassium ions. Now, this is what you are considering, only permeable to potassium ions, hence only potassium will flow across, right, that goes without saying. Now, let us look at a calculation. Equilibrium is achieved when the electrochemical potential for K plus on both sides is equal. It has to be, right, because that is your condition of equilibrium, right. Okay. So, then we can say that the chemical potential or the electrochemical potential of K plus inside the cell is equal to that outside the cell, right. See, this is very much based on what we had from before. Then your potential gradient is related to this difference in concentration of potassium ions by this equation, RT by ZF ln K plus over K plus, where the subscripts tell you which K plus we are talking about or where this K plus is. Okay. Now, remember for potassium what is Z equal to 1, right. Okay. So, if you take this example, say for K plus, this is what we saw in the other table, in the previous table, say intracellular it is 5.5 millimolar, extracellular it is 150 millimolar. Actually, I think I have the other way around, isn't it? Let me see. Yeah, I have the other way around anyway. So, I will make this EXT and make this IN. Okay. If this is the case, and if you have a certain any defined temperature, then what you will get is your potential is minus 88 millivolts, which is close to minus 90 millivolts. Now, this is what your resting potential is. That is, at rest at equilibrium, you are not looking at anything. Okay. You have a dynamic equilibrium. Even in this dynamic equilibrium, you have a difference in ion concentration, but you have a similarity in electrochemical potential because it is an equilibrium. Electroneutrality is maintained, and having maintained all those things, this is a potential which you measure, and that is how it comes out. This potential is by no means small. Let me tell you this potential is by no means small, and a small change in potential can give rise to a cascade of signaling events, and that is why these potentials are so necessary, right. But for this we did not have to know all these things. What we just derived was from our basic principles of thermodynamics, that is it, applied to physiology. Okay. So, I will just go to the salient points and then come to the main one. So, one is the potential difference results from diffusion of permeable ions. Remember, these are permeable ions because they have to diffuse, they diffuse to the ion channels, right. Now, the difference is generated if the membrane is selectively permeable to one ion only. Okay. At equilibrium, there is no net flux of K plus ions, it is already equilibrium. the system is at thermodynamic equilibrium where diffusion is balanced by potential difference. Now, that is what you have to have, because what is the net flux? Your net flux is equal to, is composed of two things. One is your concentration gradient diffusion, and the other one is your potential gradient. And in equilibrium, what will happen to the flux? That flux would be equal to 0. That means these two would be balancing each other out, and that is what you mean here. Okay. And obviously, electrical neutrality is maintained. So, these are the salient points based on Nernst equation of any membrane potential or of any potential you are talking about associated with the membranes inside. Okay. If you would ever look at these, and especially the potassium ion channels, the structure was solved, a person got the Nobel Prize for this, right, that is why it is so important, and it is really interesting to read, it is really worth reading. So, look that up. Okay. There is if you just go to Google, there is a Nobel lecture, the person who won the Nobel Prize, I am not telling you the name. Does anyone know the name? Anyway, just look that up. You look at his Nobel lecture. If you do not have it, you just let me know. I mean, I think it is one of the best notes on, the best things you can ever go through. He actually goes through how the potential channel was discovered. Okay. Try doing that. Okay. So, what we will now do is, I will come to the main topic, which is ion flow. Remember, we always talk about flux. We always talk about flux. So, when we talk about ion flow, what we say is, we say what is the force, on a charged particle. What is the force on a charged particle? Now, this F is given by F is equal to Z times E, Z times small e, which is the charge, times big E, which is the potential or the electric E field. So, this is equal to what? What was F equal to? Do you remember what was F equal to? F, just in general, your F is equal to minus dV over dr or dV over dx. Do you remember, it is a potential gradient. So, in this case, what will E be equal to? So, E will be equal to your electrochemical gradient, the electric field essentially will be equal to your electrochemical gradient. Okay. So, this is number 1. Okay. Now, when we did the Einstein-Smoluchevsky equation, remember when we did the Einstein-Smoluchevsky equation, we also knew this. We also knew that if an ion is moving to solution, say that means for a diffusing species, I have F is equal to, if you have friction coming in, what will that be? Do you remember? Xi times V, isn't it? Where xi is the coefficient of friction and V is what? The velocity of the particle. Okay. Right. Now, I can say F is equal to, if xi is the coefficient of friction, what I can write is, I can write 1 by u times V, this is 3. What is u? U is the mobility, because if xi is the friction, then the inverse of this has to be the mobility, right. Now, see, why am I talking about mobility here? I am talking about mobility here because ions will be flowing, right. Ions have to be mobile, and there is something inherent related to it. It is called conductivity. Conductivity is related to what? The mobility of your ions, right. Remember H plus, OH minus ions, these are so highly conducting, that means they are so highly mobile, and there is a reason for that. Okay. So, that is why we now move from a friction to the mobility of the corresponding ion. Okay. So, from here, from here I can have f is equal to 1 by u times v, right, no problem, that is what we said. So, this is say number 3. Okay. So, we have related two things, we have related the mobility to the force, the friction force, where F is equal to 1 by u times v. Now, this we know from before. Now, we also have a force from before, right, that means we just said equation 1 was force is equal to z times E times E. There is another force which the charged particle is facing. Now, can we combine these two forces? Okay. Now, can we combine these two forces? So, how do we combine these two forces? What we say is that how do we define flux? How do we define flux? Remember, flux was given by this very simple but fundamental equation, C times what? C times V. Okay. So, let this be equation 4. Right. So, remember, we are finally going to relate flux to your potential gradient, okay, or electrochemical gradient, that is what we are going to relate it to. If it is C times V, okay, now from say 3, what is V equal to? Good, it is u times F, so this is 5. Okay. Now, use 5 and 1 in 4. You know what V is, it is equal to u times F, and you know what force is on a charged particle, it is given by equation 1. Okay. So, then what is your J equal to? So, J is equal to C times u times F, right, C times u times F. Now, what is F from 1? So, it would be minus Z E C u, then del psi over del of x. So, this is J, and let this be equation 5. Okay, 6. So, here what you have done is you have related your flux change to your potential gradient. Before that, you had a flux change which is related to your concentration gradient, but here you now have a potential gradient coming into the picture. Okay. So, this can be rewritten as J is equal to minus kappa del psi over del of x. This would be say equation 7, where this kappa is equal to Z E C u, and it is related to the conductivity. It is related to the conductivity of your ion. Okay. So, this is the flux because of your potential gradient. We have no concentration coming in here, remember, there is no concentration issue. We started with the force on a charged particle, then we said that force is equal to V by u, which is I times V, which is V by u, and then we took this and said J is equal to C times V, and we combine all these equations to get this, right. Now, what happens when you have both diffusion and potential gradient? What happens if we have both diffusion and potential gradient, and how can we modify our equation? Okay. Diffusion of any molecule is based on concentration gradient. For a charged molecule, it has to be based on electrochemical gradient, which is del psi over del of x. So, that means based on this, can I write this, that the flux of any given particle P is equal to, one is we have just seen, which is minus kappa del psi over del of x, right, that is we have just seen, but that is because of the electrochemical gradient, right. Now, what is the other term? It should be coming from where? Minus d, then del C by del x. Okay. And remember, we are all considering in one dimension. Okay. So, see this, because it is a charged particle, it has to have, well, if it is a particle, it can respond to a concentration gradient, it can respond to a potential gradient. If the particle is neutral, it will not respond to the potential gradient, then what will it respond to? It will respond to only the concentration gradient. So, in this equation, the last term for a charge for a neutral particle, not charged particle, would be 0, because it is not responding to that, does not matter. So, it will respond to only the concentration gradient. However, if it is a charged particle, a charged particle might respond to both, right. There would be a concentration difference and there will also be a potential difference. So, it would be a combination of these. Okay. Now, when we consider, so when you consider the flux of a charged particle, when you consider the flux of a charged particle, it is given by J C, where C stands for the charged particle. Then what happens is, I can say that J C is equal to Z times E times J P. Why? Because if you are talking about a charged species, you have to multiply the flux by the respective charge, because this one was just like that. This one was just of any species. Now, if it is a charged particle, then the charged particle will always be carrying this Z times E amount of charge along with it. So, the flux is a charged flux. Hence, if I say, so let this be equation, what would this be? If this is equation 8, this is equation 9, then using 9 in 8, we have J C is equal to Z times E minus D del C over del x, okay, minus kappa del psi over del of x. Now, I will put in the actual values, that means the actual expressions. So, for example, if I say this is minus Z times E, okay, I take the minus out. What can you replace D by? I want to get rid of D. What is the expression of D, diffusion coefficient, from before? Kd by xi, right. If it is Kd by xi, but 1 by xi is equal to what? U. So, I can write U Kt, okay. So, then del C over del of x, right. And what was kappa for me? Kappa was Z E C U del C over del of x. So, you can see this flux is related to the mobility, right. So, mobility is obviously related to diffusion too. It just tells you how mobile that ion is or that specific species is. So, let me just simplify it further. Now, what I can write now is, I can take, you can see I can take what I can what can I take out? I can take minus Z E, then I can take U out, right. Then I can take a C out. If I take a C out, what I write is Kt by C del of C over del of x, and I have taken, what have I taken out? So, then I would be having plus Z of E del psi over del of x, or finally, I can write J C is equal to minus Z E U times C, this is K T del of ln C over del of x plus Z E del of psi over del of x, okay. And let this would be equation number 10 for me. So, this is the complete flux of a charged particle responding to diffusion gradient, which is a concentration gradient, and responding to your potential gradient. Okay. This is how it is written. I will stop here for today, and I will take off from here in the next class, but try to realize this. If I take this, what do you think is the term in brackets? Can someone tell me? What do you think is the term in brackets? It would reduce to just one term. How? Substitute the Nernst equation? Well, not substitute the, well, you can substitute the Nernst equation, but there is a more direct way of doing it. Just think about something, a new term, a new potential we talked about today. What was that? What is electrochemical potential equal to? Mu I prime or mu prime is equal to mu naught plus KT ln C plus ZE psi. Now, if you take, so this is a derivative of x, right, because we are talking in one dimension. If you take del mu prime over del x, what will you get? The first term goes to 0. The second term is what? KT del ln C over del of x. The next term is ZE del psi over del of x. So, that means the whole thing can reduce to what? KT del of mu prime over del of x. Okay. So, now you have taken a flux which you have given it the most general expression, it is the electrochemical potential. If there is no electrochemical potential, it just boils down to what? Chemical potential, does not matter, but that is the most general expression you can have. Okay. So, I will keep it at equation number 10, because I like the number 10, I will not go to 11 and end, right. So, tomorrow we will start from that one. Okay.